So, okay, let us continue. Our next speaker is Fang, and he is going to continue the map counting.
Thank you, Christian, for the introduction, and sorry for a long title. And today I'm very happy to be here to talk to you about some bijections between planar maps and lambda terms with some connectivity conditions. So let's start with defining the objects. So what is a planar map? Well, you have already seen a planar map in the previous talk, so I don't need to explain it anymore. It's a drawing of graphs on the plane, and then it's routed, by meaning that some corners are marked, etc., etc. Same old, same old. So I just skip this. Let's go to a more interesting part, which is the lambda calculus. These are the things that based on something called lambda terms. They come in three varieties. Either it is a variable, well, it's an atom that represents variables, or it's an application of a lambda term t that acts as a function to another lambda term u that acts as a parameter. Well, intuitive enough, but then we need to get some functions. And it's the third way that we get a function. We pick a lambda term t, and we use it as the function body, and we simply write lambda x dot t. Then it is turned into a function of the variable x. Okay? Now, lambda calculus is simply a way to manipulate these lambda terms. There are essentially two rules. The first one simply says that, in fact, the names of variables are not important at all. What is important is the association between variables and abstractions. And the second rule is the real rule of computing. That tells us when we have something of a function, something of a function type applied to another term, what will the result be? Well, simply we take the function body and we replace each occurrence of the variable x by the parameter u. So it's natural enough. Let's take an example. Consider this term omega, which is formed by lambda x dot xx applied to itself. Okay? The first part of the application is a function type. So we can do beta reduction, and what we do is that we take a function body xx and we replace each x by the parameter. Then it duplicates the parameter and we found omega again. Okay? So what's interesting about lambda calculus was that this is very simple, but it is in fact Turing complete. So we can do all the feasible computation on it. And it is also well defined in the sense that, however, you take a term, you try to do beta reduction on it, you try to get some result, and this result will be unique for whichever order of reduction that you do. So the result, we call that a normal form. Of course, when there is a normal form, if there is a result that's possible, then it will be unique. But for omega, there's no result. So if we take this example, lambda x dot y applied to omega, there are two places we can apply the beta reduction. Either we can apply it inside omega, then we'll always get back to omega, so nothing has changed. But we can also apply it for the global application, then we'll get directly the variable y, which is the result. And in whichever order you do that, you always get y, of course. Okay, so this is nice and complicated. It looks complicated. But for me, a combinatorialist, it's much simpler because I'm going to just look at it as some kind of unary binary trees. So the syntactic tree of the lambda term, with unary nodes as abstractions, binary nodes as applications, and leaves as variables. And we also need the association between variables and abstractions, because this is what's important. So instead of looking at only the skeleton, we'll also draw what we call the diagram, in which we replace each leaf like this, each variable like this, by an edge linking its parent to the corresponding abstraction. Okay? And it's also clear enough that a variable is always bounded by some abstraction before it, well, on the ancestor side. In this talk, I'll consider lambda terms that are particularly simple. they are linear lambda terms, which means that the association between variables and abstractions, they are one-to-one. So one variable captured by exactly one abstraction. And we further simplify things by looking only at planar terms, meaning that when I draw the diagram, if I draw each new edge in a counterclockwise order, we can draw it in a way that the edges does not cross. Okay? But if we think at it, if we consider terms that are linear and planar, then in fact, the association between variables and abstraction, there is only one way to do that. So that is planar. So in fact, for these terms, instead of looking at the whole diagram, which will be a graph, we only need to look at the skeleton, which is a tree. That's much simpler, of course, I think. But then you may ask me, well, this looks too simple. Why are you interested in this? I have a very logical reason, because it's related to logic. It comes from what we call the Curry-Howard correspondence, in which we essentially say that a typed program, they are equivalent to mathematical proofs. More precisely, we'll look at typed lambda calculi. Well, we typed the terms in the lambda calculus in order to avoid infinite computation that we have seen on the term omega, for example. And then, if we take such a system, they will correspond to a logical system. And then, if we look at lambda terms in this lambda, in some of these type lambda calculus, they will have some types. And in fact, each lambda term, each type will correspond to a provable formula in the logic system. And the lambda terms, as certificates, there will be proofs of these formulas. And in particular, if we restrict the lambda calculus to linear terms, what we get is the linear lambda calculus, which under this correspondence is equivalent to what we call the lambda fragment of intuitionistic linear logic. And intuitionistic linear logic is a very powerful logic that models how resources are generated and used, in which variables are considered as resources, and abstractions, they are considered as consumption of these resources, so they disappear afterwards. Okay, and this Curry-Howard correspondence is one of the reasons that we are very interested, well, logicians are very interested in enumerating all kinds of families of lambda terms. So these lambda terms are divided with various properties. I'll just introduce two that we will need in the following. A term is called unitless if every subterm has at least one free variable, meaning that there will always be some variable that's not captured inside the subterm by some abstraction. And we say that a lambda term is normal if it is a result of some computation, meaning that there's no further beta reduction that is possible. Okay, and here is a big table of a lot of known results on enumeration of lambda terms, and it is the accumulation of work of quite some people. And what's very interesting on it is that at each time we know how to count lambda terms. Somehow they are also counted, the sequence also counts some families of maps. And of course, history repeats itself. In 2019, Norm Zeiberger and Jason Reed, they asked themselves a very strange question, somehow motivated by type theory. Well, they look at planar linear normal terms and they try to figure out the connectivity on the diagrams. Okay, they try to classify these terms with the connectivity of the diagram. And connectivity here means edge connectivity, meaning that a graph is k-connected. If deleting any k-1 edges, they will not disconnect the graph. Okay? And now if we look at diagrams of lambda terms, we'll see that all these are one connected, because you have the skeleton that connects everything. Then we look at two connected planar linear normal terms. Well, it's already a bit more complicated. It's two connected, meaning that the only obstacle for two connectedness is a bridge. And on a diagram, a bridge must be on the tree. And if we look at the subterm induced by the tree, we'll see that there will be no free variable, because if there is one, then it will connect this subterm to something above. So we see that, this is bridge is equivalent to a closed subterm, and this is exactly the obstacle for unitless terms. And this shows that two connected terms are exactly unitless terms. Now for free connected, well, they didn't give a combinatorial characterization, but they did give a characterization in type theory. As you know, that's not very useful for combinatorial stuff, so they don't know. However, they still computed the first terms of the enumerating sequence, and they found that, well, it looks like that it's enumerated by this very nice formula, which also counts by part-type planar maps. So now we want to find bijection, of course. They conjecture this is true, and we want to find bijection, and this is exactly our contribution here, that we have a direct bijection between these two objects based on some combinatorial characterization of free connected terms given by Cassia and Guanru in 2020. And with this bijection, we see that a lot of interesting statistics are transferred from maps to lambda terms. And with this, we can get for free refined generating functions and even some probabilistic results. For instance, if we take a free connected lambda term that's very, very large, and then we count the initial abstraction on it, this is a random variable, and in fact, it converges to the law, very nice law described here, which means that it's exponentially decaying. Okay. This is the first result, and then using the same kind of approach, I also gave a bijection between planar linear normal terms, so one connected terms, to general planar maps. And if we restrict the bijection to unitless terms, so two connected terms, what we get are loopless planar maps, which are duals of bridgeless planar maps, which means they are two connected planar maps. So essentially, we recover these two lines of results, which was first proved by Noam Zeiberger and Alan Giochetti in 2015, but their bijection is recursive, so less easy to manipulate. And it's also on different family of lambda terms, which is less nice because they are not closed, not stable by beta reduction, so they do not form a lambda calculus. Anyway, so now these are the contributions, and now we'll look at the bijections. For the bijections, we call that, well, I will only be looking at unary binary trees because we have said that linear planar lambda terms, we only need to look at this skeleton. And for this, I'll need some statistics. First is the number of unary nodes, so the number of abstractions in a term. Second, the number of leaves, which are the number of variables. And the third one is the most important one, is the excess, which is simply the number of leaves minus the number of unary nodes. And for lambda terms, they stand for free variables, meaning that they are variables that are not yet captured by abstractions. Okay, now we can describe all the families, one connected, two connected, etc., using this excess. A term is linear, meaning that we have the same number of variables and abstractions, so it means that its excess is 0. And a term is one connected, so well-defined in some sense, well-scoped, if for each subtree the excess is positive. This simply means that each abstraction will have a chance to capture some variables. Okay? Two connected means that there is no closed subterm, which means that for all proper subtree, the excess is strictly positive. So it's equivalent. So we see that, well, the properties, the one connected, two connected, they are easily described by excesses. Now we try to characterize free connected terms. First, we start with a small observation. If we take the skeleton of a free connected term and we look at its first binary node, then its left subtree must be a leaf. Why? If it's not a leaf, it's a real tree. Then there will be free variables because it's free connected, so two connected. And then if we also look at free variables on the right subtree, then they, by planarity, they will be absorbed by segments of abstractions just at the beginning. Okay? And now we only need to delete this edge and this edge to disconnect the diagram, which is not possible because we are on free connected diagrams, with free connected terms. So this left subtree must be a leaf. Okay, once we know that, we only need to, in fact, we only need to consider the right subtree here, because once we know this, to recover the whole term, we only need to add the binary node, add a leaf, and then add all the abstractions we need to capture all the free variables. So now the real stuff, the real characterization on free connected terms. So a unary binary tree, S, is the reduced skeleton of a free connected term if and only if the following two conditions are satisfied. The first one is the normality condition, saying that the left child of any binary node must never be unary. Why? Because the left child of a binary node it stands for the first term in an application, and if it's unary, then it's of function type. In this case, we can apply beta reduction, which is not possible because we are on normal terms. They are results. We should not be able to compute from it. So this says that, well, this cannot happen. The second condition is really for free connectedness. It's simply that if we take a binary node like this, and we count the number of consecutive unary nodes above it, this should be strictly smaller than the excess of its right subtree. Why? Because if it's not this case, then the free variables in the right subtree will be captured by a consecutive segment of abstraction just above the binary node here, and we only need to cut this edge and this edge to disconnect the diagram, which is not possible because we are free connected. So we see that this free connectedness condition is a necessary condition. However, it's a miracle that is also sufficient, and it takes 2 pages of case analysis to prove. Okay, once we have the characterization, we can do the bijections. And for this, I will need a new model, well, intermediate model called degree trees, which is simply a plane tree with labels on its nodes. If it's a leaf, then it will be of label 0. Otherwise, we'll look at each child will contribute something, and the contribution of each child will be 1 for the child itself, and the label of the child. Except for the first child, because we know that in every culture, the first child is somehow important, somehow distinguished. It is allowed this time to retain some of the contributions, and the maximum it can retain is its own label. So, for example, if we look at this node here, it has 3 children with a sum of label 5, so the maximum label it can have is 8. However, the first child, it can retain something up to 5. So the minimal label for this node is 3. And in this case, it's 6, meaning that the first child has retained 2 contributions. And just to remember it, we can put a label on the edge linking this node with its left child, with the label, with the quantity of contribution that's retained here. And if we think a bit about it, we see that, in fact, we only need these labels on edges to recover all the vertex labels, because we can always compute from downside up. That introduces us to the notion of edge labeling, and we'll use interchangeably the edge labeling and the vertex labeling of a degree tree. Okay, now the bijection in 1 minute. It's doable, it's easy. We take the skeleton, we delete the leaves, we remove the unary nodes, but just to remember, we will put a small label on the edge that we obtained for the number of unary nodes we remove. Then we perform the bijection, usual bijection between plane trees and binary trees and plane trees, saying that the left child in the binary tree would be the left sibling in the plane tree, and the right child would be the rightmost descendant. So we get plane trees like this, and because we are on normal terms, the unary nodes are always on the right-hand side of binary nodes. So it means that the edge labels are always on the rightmost descendant edge for each node. We flip the tree, they're in a good position for edge labeling on degree trees. And indeed, this is a bijection. To see that it's not so complicated, first we admit that the contribution of each node will be the excess of its right subtree. And then if we look at this node here, for example, it will try to retain some of the, its first child will try to retain some of the contributions, but the retained contribution will be the unary node here, and by the free connected condition, this cannot exceed will be strictly smaller than the excess here, which translates to the fact that we can retain at most the label of the first child. Okay, this is the first part of bijection. Second part of bijection, in fact, it's an existing bijection between degree trees and bipartite maps, which is essentially an exploration process on the bipartite maps. And in fact, it was a submission of FPSAC 2021, which relates bipartite planar maps with Chapeauton's new interval of, in the Temeray lattice. And there are also interesting statistics that are transferred in using this bijection. And that's how I get the probabilistic result that I mentioned before. So conclusion, the second bijection is more or less the same thing. And I'm looking at there are further directions we can looking at, for example, high connectivity or other enumeration consequences. But there's one particular thing that I'm looking at what is interesting for logicians are what we call the principal types in the planar lambda calculi. Their enumeration starts like this, and if you have any idea on what these numbers are, I would be very interested to know. Thank you very much for your attention.
Thank you. Thank you very much. So there's time for a few questions.
Yes, please.
In the original table, there was a connection to free flows, which is what the norms paper. What's the connection between the flows and the maps?
This one? The question was, what is the connection between flows on free valence graphs and lambda calculus? The flows are not exactly flows. The flows is a way to express a kind of typing procedure. In fact, they are not numbers, they are types. So, yeah.
Another question?
Are these sequences D-finite?
The question was, are these sequences, I believe it's the last one that you're mentioning, or all the others? Okay, let's take the example in the table. In general, if they are planar maps, then they are even algebraic. Okay, however, if it's not planar maps, in general, it would be maps of arbitrary genus, and in this case, we don't have guarantee on definiteness. And for this one, I don't even know the enumeration formula, so I have no idea what it is. So, yes, please.
More generally, if the planar maps have a meaning in logic, does the genus of a possibly non-planar map have a logical meaning?
This in fact, okay, the question was, as planar maps, they have meaning in logics, then genus, does it also have a meaning in logic? The answer is we don't know. This is something that is in active research. We have been trying to invent lambda terms or lambda calculi that reflects the genus, but for the moment it was not yet very successful, and we doubt that maybe the good notion of genus, or in some sense in lambda calculus, it would be exchanges of variable. We would probably need something that is a bit different than a genus to get a nice lambda calculi.
Okay, thank you very much.